All right, so maybe just to summarize what I showed you on the previous screen, just without so many of the d orbital diagrams on it. Iron has 26 electrons. All right, the electron configuration would be to say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. All right, now total the exponents. In this case, 26. If you go and you count the electrons in iron, well, how could we figure that out? Well, in a neutral atom, electrons and protons are equal. The atomic number, so the number of protons of iron, is 26. Therefore, a neutral iron atom must also have 26 electrons. When you write an electron configuration, the exponents, okay, so shown on the screen in red, all right, they must equal the number of electrons. All right, it's a quick way to check and make sure that you've got the electron configuration correct. All right, so you can have a look right here and notice the prompt I have written on the screen. Draw the orbitals and electrons of iron. So let's switch off of this screen. All right, and what I've done is I've gone ahead and I've actually drawn all of the orbitals on their own. All right, now one important thing to note here that maybe we haven't really discussed at this point is that orbitals at the same value of n, so at the same principal energy level, are the same size. Meaning the 2s orbital has the same diameter, so that sphere has the same diameter as if I was to measure from the top, let's say, of the 2py orbital all the way to the bottom of it. They are the same size. All right. As you move down the periodic table, the orbitals get larger. All right. So in Science 10, you would have discussed valence electrons, and someone would have told you that valence electrons are the electrons that are found on the outside of an atom. Why are they? How do they get on the outside? Well, the orbitals in which they're found are larger than those that are what we'll later come to call core electrons. Okay. So a valence electron is the one on the outside. All right, and this is also going to be some explanation as to why we like to say all of the transition metals have 2 valence electrons. All right, so I'm going to move some things around and try to stay with me on this. All right, so first of all, I have remember the final electron configuration of iron from the last screen ended as 3d6. All right, so you can see here my d orbitals drawn in red. All right. I've got my electrons in them. I have 1, 2, 3, 4, 5, 6 electrons. So this is 3d6. All right. I'm going to layer all of the orbitals on top of one another. So here we have the 2s orbital surrounding, okay, the 1s orbital. All right. And now I'm going to go from 2s, I'm going to move over to 2p. Notice how they're the same size. Okay, I'm going to go to, so that was 2py, I'm not doing this in any particular order, 2py, 2pz. Okay, and I'll move them in. So there's 1s, 2s, 2p. All right, I'm going to need a little bit more room, so I'm just going to move this over to the center again. Okay, what comes after the 2p orbitals are filled? Well, 3s. 3s, okay, is larger than any of the 2 s or p orbitals. All right, once 3s is filled, here comes 3p. Notice the 3p orbital is drawn so that it's the same size essentially, all right, as the 3s. All right, so we'll make all the 3p orbitals slide in there. Okay, so now those are layered on top of one another. I'm going to need a little bit more room again. All right, the next orbital after 3p, all right, so have a look at your periodic table. All right, we move from 3p, we come to 4s before we get to 3d. So 4s comes here, surrounds everything that's already in there, and then we're going to have to move over into scandium, titanium, vanadium, chromium, manganese to get out to iron. All right, watch what happens with the electrons from or found in the d orbitals. They actually are smaller than the 4s electron. All right, they actually end up going inside. They're the same size essentially as the 3s and 3p electron. Alright, so they sit inside the 4s shell. Alright, like this. They're all about the same size. Alright, and I'm going to move them together here.